Thank you very much. So the boring, originally submitted title of the talk is Shared Objects and Content Addressing, a Survey of Techniques. There's another possible, alternate, spicier title, which is Shipping Fearlessly on Any Linux with exactly your libraries and on-disk dedupe, too. I'm a Linux user. Spoiler, I will focus on Linux a bit in this talk. Really sorry if that's an unpleasant surprise to anyone. And something else I'm going to try to accomplish throughout talking about library management today is how to ship things without asking permission from anyone, without the need to argue with upstreams, argue with downstreams, or argue with any other streams in any direction at all. I'm Eric, and I like reproducible builds, but I'll skip ahead on that. I'm going to buck the trend of the day as well, and I'm not going to talk about a package manager. I am going to try to talk about a quest for radical simplicity in how we handle files, and search for conventions that we can share, hopefully amongst many different package manager approaches. And I'm going to focus a lot on things that are easy and require minimum amounts of coordination, because things that aren't easy don't get adopted, and I like to work on things that get used. Ease can, of course, be a complicated topic, and there are many different kinds of ease. We could focus on the ease of building software, on the ease of packaging it once we've built it. We can focus on the ease of installation and how users experience the acquisition of software. And we could even talk about the ease of debugging and the confidence of knowing what we have. I'm not going to talk about all of these because it's not that long of a talk. But I will spend some time focused on the ease of packaging and the ease of the user's experience of getting that packaging. And there is one more philosophical bent that I'm going to have, which might show up a little bit, which is that user choice matters. I really want control as a user of software over which software I select. And I don't want to be living within some system that dominates my ability to choose. So I'm going to have spicy opinions about Linux distros. And I'm going to seek things that have simple, independent parts and try to find ideas that can be assembled. I have a very janky cable here somewhere. So in this talk, I'm going to talk about what are shared objects, what does that mean, why do we have them, do a little bit of inspection of what normal looks like now, talk about what could be different and what could be better, such as finer cables, and then try to really get a hang of my ultimate goal is going to be ways that we can collaborate when building and shipping software without needing to coordinate. Not that other people aren't nice, but the more you can get done independently, the more productive you can be. So, in that background section, when we package software, there are some pieces that appear repeatedly. Sometimes it'll be plain data, sometimes it'll be libraries. The common thread of what I mean by shared objects is that there are these independent pieces that aren't the main application file, and sometimes they are shared with several applications, and when that happens, ideally, we want to ship those things once when we're putting together whole systems with multiple applications. What exactly that means will vary based on what kind of software you're working with and on what kind of system you're distributing it. So always you're going to have some main executable binary, always. If you're on Linux and you're working with C-type applications, you're almost certainly going to see a lot of .so files, which stands for shared objects, which just means bundles of precompiled code. But there could be many other kinds of files as well. There can be just raw data files. There could be a time zone database. You have different extensions when you're doing this stuff on Mac, but it's semantically very similar. You could have jar files. I cannot possibly cover the entire breadth of this stuff. So in this talk, I'm going to focus on files in general wherever possible, but then when I want to deal with a really gnarly problem, I'll talk about how .so files have to be handled because they are hard. So the good thing about having software that can be split apart into reusable pieces is that it helps us, at least in theory, ship more compact systems with more shared parts. So when you get your Linux install, you have all of the little executables, and you have all the little shared libraries, not too many copies. It means your whole thing fits in a reasonable amount of disk space. That's good. Shared objects are also somewhat unavoidable. And I don't know if I can really unpack this topic because it's a bit large. But static linking doesn't work all the time. It's weird. Sometimes you can just add -static to your compilation flags in your toolchain, and it'll work. And sometimes it won't. The reasons for this are weird, long, complicated, but take my word for it. Sometimes you'll discover that you need to like patch an upstream of an upstream in order to get static linking to work. And I run out of time in the day sometimes. I don't know about you. My days usually have 24 hours, and I like static linking. So we will work with shared objects when we ship applications. But the bummer is, this can make stuff really complicated. Complexity starts slipping in, basically the instant we start trying to share stuff. And, well, why? Why does complexity slip in? So I'm going to dive straight into some examples of what stuff looks like. I don't know how many people in the room actually do see library management often, but here are some of my favorite commands to inspect what the heck the system is about to do and what it just did or will do. Readelf is a command which will inspect headers in a Linux executable file. And LDD is, can I wiggle this in some way? This is really nasty. Okay. LDD is a script which will ask the part of a Linux system that loads dynamic libraries for you what it's about to do. So these are two ways you can inspect how an application is going to run on a system. When we have shared libraries, they are identified by a part of a header of an executable file, which has just this textual string naming the library here. And when we have the dynamic loader on a Linux system take a look at this executable and decide to try to run it, it comes up with a couple things. The first and the last thing on this list are a little bit magical, and I don't really want to dive into them today, but these middle two are those same library names, and on a real system they'll get resolved to some path that looks roughly like this. This is normal. Ooh, too many slides. So the things to notice in this are there is a major version number in the library name. It's attached at the end there. And these paths that get resolved, they get resolved to a global path, or an absolute path, based on a global search. And this is based purely on the library name. So I don't love this. This does not leave us a lot of flexibility, and it sets us up immediately to have coordination problems when we try to ship software on Linux. Because we have the major version number in the library name, well, that's not bad per se, but it's all that we have. That's the only information that we have to go on. And when you combine this with a global library search path, this de facto means you cannot have multiple versions of libraries on your system unless you're bumping whole major versions. That produces whole discussions with large groups of people, and it means you have coordination problems. The end game effect of this is if you want to ship software on Linux, you get dragged into large conversations with many different groups of people in many different package manager communities. You have difficulty getting the latest versions of libraries. Your application might get shipped with different versions of libraries than you and upstream have actually tested with. This is why we cannot have nice things on Linux. Yeah, someone in the crowd just says, it's true. Yes. This is why we have 900 million Electron applications on our systems, because that's the one way you can kind of, for that one example, get away from this. So can we do something better? I want to have fewer arguments when I want to ship stuff. And I want Linux as a whole to have more people shipping to it. Two sides of the same coin. I was going to rant for a little bit more about symbol collisions, but like everybody's seen library symbol versioning go wrong. I want to not have these problems anymore. So I think it's well established now. The system package managers have not set us up with solutions to this. When we have a system-wide package manager on most Linux distros as we know them, this turns into a swept-under-the-rug problem. If you accept the embrace of the system package manager and their choice of library versions, then you can have an OK life on that system. But this doesn't scale. If you want to ship stuff, you now have many conversations to have. It's sociologically intractable. It doesn't work. We need to try something else. Brief breather. What else could we try? So, harkening back to just technical brute facts at the bottom, I think the seeds of our demise were already planted, like, at this very early state. It's that major version number. This is actually where we've all gone wrong. There is that major version number. We expect it to go up. That means you have to talk with other people about the number in order to make sure that it's monotonically increasing. That number is not enough information. People can debate the virtues of semver, but I think it's just clear people do ship things that cause ABI breaks, and then they don't bump a version number. This happens more than literally never, so it's a problem. And ultimately, people want to make changes to software more often than they want to deal with all the conversation spawned by bumping a major version number. But some of these problems... Wild. OK. You see, I have no live demos in this slide, so something else has to go wrong around the talk. Anyway, I think there's a pattern that we could lift from this where we see a number, and the number isn't enough. We've encountered this before in the realm of version control. We used to have version control systems where we used numbers that we decided would monotonically increase. We don't do that anymore. This is already rapidly consigned to ancient history, right? SVN, it's gone. The answer in version control was stop using numbers, start using hashes. And since we've had that essential lesson, we have Git and Mercurial, DCVS. There are several other ones as well. Git kind of took over the world. But all modern version control systems, in essence, use hashes because they solve problems. Hashes instead of version numbers means we know exactly what content we're targeting. There are no mismatches. It just removes whole categories of problems there. And hashes have this extremely magical trait of being able to be chosen without coordination, without any conversation with anyone at all. And they still don't collide. Cryptographic hashes, obviously. So let's use this. Can we combine library versioning and the concept of version control with hashes and get a nice world to come out of it? What could go wrong? I might be setting you up to think that lots of things will go wrong. No, actually, this kind of works. If you imagine this existing stuff, you've got library names there, they're absolute paths, and you just change it so that those library names are hashes of the library file. It works. You can just do this. They're just strings. It really does work. It doesn't solve everything in the world that I want to all at once, but it has some really neat properties. If you do this, you can now have exact versions of libraries, and they can be co-installable on the same system. Because they have the content addressing hash, duh, you can put a bunch of them in the same directory, and it's fine. You can just do this. It'll work. This will let you have infinite numbers of versions of libc, for better or for worse. But it will let you do it. Now, there are some things that are not perfect about this. If you now want to change the library versions, these headers are in the binary, so you have to edit the binary to change them. That's maybe not ideal. And it doesn't explain itself very well. So now if I use LDD to inspect one of these executables, you get just the big hash in it for the identifier, and then the big hash again where it was found. This happens to be the hash of libtinfo, You can't tell. So that's not helpful. Like, the sysadmin in me does not love that lack of information. And we still have this global search thing. So if, like, let's say I wanted software that I could install in sort of a drag and drop way as an end user without needing any kind of pseudo or privilege escalation to write into a global shared path prefix. I haven't solved that yet. But maybe we can. So let's take another look at this and then start with that global lookup thing, because that seems to be a bit of a problem if I want to have like drag and drop installs without root. I need to fix that global lookup. Turns out there is a thing for this. This is already widely distributed in all of the ELF interpreters and library loaders. You can use a very magical header called an rpath header and set it to include this magical string, $ caps lock origin. This can be a little tricky to wiggle through build tools, by the way, because it looks like a shell variable, but it's not. Mind your escaping. If you successfully get this into a binary, it'll show up in readelf as another entry, like so. And my favorite string to set it to is actually $origin up1 lib. So this tells the library loader to start from where the binary is, go up a directory, because it's probably in a folder called bin, let's say, and then go in another folder called lib, and look for your .so files there. So that lets you ship a file system that looks topologically like this. So you could have your bash, for example, put your libs next to it, just like do that, copy the whole files there. And that'll work. That you can put in a tarball, give to somebody. It's going to run. And if you ask LDD what it thinks of this, it doesn't actually get very surprised at all, because like I said, this concept of $origin, been around for a while. It's just not widely known. So it'll tell you something like, it'll still show you an absolute path. But you see this /lib, that's coming from your rpath header. This changes. So you can move that directory around, and LDD will tell you an absolute path, but it'll change on the fly. You do not have to rewrite the binary for this to happen, by the way, which is, there are other ways you can do this that usually do involve rewriting the binary. This is more flexible. So this is one of my new favorite ways to ship libraries, because it kind of just works. This really simplifies things drastically. And it's very legible. The headers still said the names of the libraries that we were using. That's nice. The sysadmin in me likes to still have that information around. But it's not entirely perfect because I just said, oh, let's just copy the whole library files. Oof. I mean, we can. Disk is relatively cheap most of the time. But like, that's still wasteful. Let's be better. So we've now briefly looked at two ways to go about stuff. One of them is this very simple, very legible, easy to ship thing where we copied the libraries. Not great. And the other was this earlier peek at using the hash of the library as the library name, which was coordination free and could like support multiple library version installs and even do deduplication. If different people were using the same library, it just naturally does the thing. But it had this fixed prefix need, and that was kind of a bummer. So can we just do both? I think yes. I would propose that you can do this with symlinks. There's probably other ways to do it as well, but this is the one that seems the most powerful to me. We can combine these traits. We can have the $origin in the ELF headers, so say, like, look next to me for the libraries. And then in those paths that are adjacent, use symlinks. The symlink target can contain the content addressing hash. This will let us share things and deduplicate them, coordination free because it's a hash. And it still explains itself. And yeah, okay, green text for all the good traits. Dedupe, exact versions, co-installable, clear, says what it wants. And this works at any install path. If you take a whole file system like that and you open it anywhere on your system, it just works. This is kind of cool. At some point, I should present downsides of this, except I'm not aware of any. There is one more thing, even on top of all of this, that you can do. If you want to, let's say, handle your main executable and all of your libraries as a series of independent but read-only file systems. You could snip right about there where I've put the carets. You can ship each of those file systems and mount them as long as they're relative to each other. You could have, like, let's say you're about to have a container environment, and you have a series of content addressable caches of partial file systems, and you want to mount those into the container with simple bind mounts. You can do that, and it will just work. All of your bind mounts can even be read-only, and it will still just work, because remember, we did not have to edit any of the executables on the fly, and everything is naturally converging because it agreed to use hashes for where these things should go. That is really neat. The mechanical sympathy on that is very high. So that was the secret goal that I had this entire time. It happens to work well in these container scenarios where you want, for convenience and speed, let's say you just really love this read-only stuff. It happens to work trivially well if you take the same thing and you copy it to a USB stick. I work on another project called WarpForge where we do have a assemble a file system syntax where this just happens to work perfectly. You might be thinking of projects which have tried to do easy composition of systems and executables by using union mounts, or now we call them overlayFS, where you can stack up many layers of file systems. This is a little different, right? Because we're stacking a bunch of file systems as siblings, where the mount depth there is 1. It's just a bind mount. Whereas overlayFS stuff is building these layers. overlayFS has scaling problems. If you have this many layers, any I/O operation has to bounce through all of them to see where the actual file is. And it also still has coordination problems because you're sharing one root, right? With this approach of using hashes for the library addressing, we don't have to have a single shared root. We can all just agree to not collide by using that organizational mechanism. Now, I said we were going to do this with zero coordination. And that was a bit of a fib, because I've been throwing hashes around. But what exactly do we hash? That is actually quite a tricky question. And it's not one that I'm going to fully answer. This will be a turn it over to the audience time. There are many different possible parameters in hashing. I can at least try to enumerate them, and this will be a discussion starter. So maybe we like SHA-256, or 384, no length extensions. Or Blake, there's not actually a Blake 5000, but there are many variants of Blake. If we're turning hashes into a string, so we can put them in the file system and in these ELF headers, we have to turn them from the binary number of the hash to, well, a string. So base 16, hex, OK. Or base 32, a little more compact. Base 58, I like it, but now we have to agree on that. And in the easiest possible mode, the hashes that I had on the screen earlier, they were real, but they were just file content. They were just the SO files. So that removed a whole question, right? But if we want to hash directories, how do we do it? We have to mark the leafs versus the nodes, right? The files versus the directories. And we have to encode the path somewhere. So now we have to design a whole Merkle tree. This is easy, right? You just design a Merkle tree. But if we want to share a bunch of work among the whole realm of people doing package management and shipping software, if we can pick one way and agree on it, it will save us from ever having to coordinate again. It would be nice. I can dream. Other questions might include what attributes of the file system do we want to talk about, right? For .so files, the answer is basically nothing. But if you want to generalize this to all file system segments that we might want to share, what of the range of POSIX bits do you actually want to talk about? Like all of the read, write, execute for all three? Do you want to talk about the UID? Maybe not. Do you want to talk about the sticky bit? Maybe not. Xadders? Oh, God. And another one that comes up as a possible point of desynchronization is whether we want to include package names in paths even when we are using a hash as part of the sharing mechanism. Now, this is an interesting one because, well, I don't know, my naive take would have been, no, that doesn't help. But basically every system that I've seen in the wild, does decide to do that. Nix has a mangle in their name. It's not a content address usually, by the way. And then it has the package name. So you can do like stuff in your shell and like tab complete, and it kind of does what you mean. It's nice. It doesn't help us deduplicate, but it's nice. I saw a SPAC example on the screen earlier today that seemed to do the same thing. So this is very popular. Whether it's a good idea or not, I don't know. I guess it must be. Please discuss. I do not have answers to these questions. I can only raise them. I will mention one possibility that comes to my mind. Git has a tree hash, which happens to have files, directories, file names, the X-bit, symlinks, and nothing else. I hypothesize that that is like pretty close to what we want for sharing shared libraries and most things I can think of in packaging. Maybe this is good. I'm not sure. If anyone wants a freestanding implementation of this, by the way, I found that this particular piece of the Git plumbing was hard to like find direct access to, so I wrote one freestanding. It's like a one-page piece of code. It's pretty easy. With that, I'm about out of time, and onto the Q&A slide. So thank you very much for your attention. I hope this was useful, and there's some reusable bit of idea buried in here.
One question. I saw your hand first.
I know one downside of $origin frequently highlighted security reviews is that it makes it easy to inject a compromised library binary relative to the executable binary, whereas if the search path of the library is an absolute, usually userlib is mounted on a read-only file system that's harder to tamper with. What kind of mitigation would you need to come up with to resolve this in this approach? Thanks.
I don't really see it as that much of a direct security threat any more than I see like the presence of shell scripts in my home directory as a security threat. It's like, yeah, if you own the file system and you can write to my executables and libraries, then you can win. That's kind of the nature of like having computers that are based on Turing machines, right? I don't want to dismiss it, but like, yes, anytime you have executable code on your computer, you need to make sure that whatever access control mechanisms your computer supports are applied on that code. I'm not very happy with what those control mechanisms are on any kernel on Earth I've ever seen, but such is the world.
All right, thank you.